This is the second part of the third session of our course, Introduction to Differential Geometry. We are going to continue studying submanifolds in this lecture. This lecture is slightly more proof-based. So we started studying submanifolds. So let's say we have two manifolds, M and N. Let's say M is an m-dimensional manifold sitting inside another manifold n, which is n-dimensional. We gave two definitions of what it means regressively, what it means for M to be a submanifold of N. The first one was using local model, right? So local model was the first one. So let's say this kind of larger manifold is N, and then inside N we have M, another smooth manifold. So we say it's a submanifold if for every point X in M, there is a small open neighborhood, say U, inside N, and a diffeomorphism phi such that maps U to an open subset or to all of Rn, right? With this extra property that if you restrict this map phi to M, to the intersection of U and M, this red chunk, phi of U intersection M would become Rm sitting inside Rn. So it would be Rm intersection with the image of phi. That was the first way of defining submanifolds, right? We had a second way of defining submanifold. So the second definition would be kind of using the inclusion. So we have an inclusion, just natural inclusion, because M is a submanifold of M. So iota, we have natural inclusion from M to N. We say these two, when we have inclusion between these two manifolds, we say M is a submanifold of N if this inclusion is an embedding, right? So now what we are going to discuss in today's lecture is that these two definitions are equivalent. So the first one implies the second one, and second one would imply the first one. So we are going to prove this. So today's lecture would be on the proof of this fact. And yeah, if it's the first time you see this proof, it's better to understand the big picture and that kind of you can work on the details to get a better understanding. So let's start by showing the first definition implies the second definition. So let's say if M is a submanifold of N in the local model sense, then M is a submanifold of N in the inclusion is embedding sense. So the first definition implies the second definition. Let's prove that. Okay, so in order to prove this, I should show the inclusion from M to N is an embedding, right? So this map, I should prove, is an embedding. So what was the definition of embedding? Embedding is an immersion. So the first thing we learned about embedding is that it is an immersion. And the second thing we learned is that if we kind of look at this immersion from M, but if we restrict the codomain to exactly the image of this, so rather than taking the whole N, consider iota of M inside N, this map should be a homeomorphism. So if this map is a homeomorphism, and we have iota is immersion, iota would be an embedding. I'm going to kind of prove the first part. Today I'm going to show iota is an immersion. That's what we are going to do today. The second part, I'm going to leave that to you as an exercise. This is not very challenging. So let's just focus on the first part. Okay. What does it mean for iota to be immersion? It means for any point in the domain, any x in M, derivative of this map at x should be injective. So it's a map from tangent space of M at x to tangent space of N at iota of x. So I should show this linear map is injective for any x in M. Okay, if I do that, then I get this map is immersion, is an immersion. Okay, great. So our assumption is that M is a submanifold of N in the local model sense, right? So what does it mean? It means we have M and the map iota to N. So let's pick any point in M and look at the image in N. Just by the fact that these are manifolds and they satisfy the local model definition, it means there is a small open subset U containing X in N, and such that if you restrict that to M, if you take the intersection, you would have the local model. So there should be a map phi, a diffeomorphism from U to Rn, such that when you restrict phi to U intersection M, you get a map to Rm, a diffeomorphism to Rm, right? This just comes from the definition that M and N are manifolds and one is inside the other. The local model means the map from Rn to Rm to complete this diagram is given by the canonical immersion. So what do I mean by canonical immersion from Rm to Rn? Take a point in Rm, let's say it's given by coordinates x1 up to xm. Canonical immersion takes this point to x1 up to xm, n must be greater than or equal to m. So there are some extra components. Just fill the n minus m remaining components with 0. This is called canonical immersion. Local model means this diagram commutes. What does it mean to commute? It means it doesn't matter if you go from first iota, if you say pick a point in U intersection M, apply iota, and then apply phi, you would end up in Rn. Or you can start with phi, go down, and then apply the canonical immersion. You again would go to Rn. Doesn't matter which path you pick, you would end up at the same point, which means phi composed with iota equals canonical immersion composed with phi. Okay, that's what it means to have the local model. That's literally writing the local model using these maps. Okay, so why does it imply iota must be an immersion? Well, we can apply phi inverse since it's a diffeomorphism on some small set. We can apply phi inverse on the left of both sides of the equation. So iota would be phi inverse O canonical model of phi, right? Now using chain rule, we can take derivative of both sides at the point x. So derivative of iota at x would be derivative of the maps on the right-hand side, d of phi inverse or d of canonical immersion or d of phi at corresponding points. X, canonical immersion applied phi of x and canonical immersion applied to phi of x. Let's just ignore that. The point is that phi and phi inverse define on correct subsets here. They are diffeomorphisms. And the derivative of diffeomorphisms at given points are isomorphism, which is injective. Canonical immersion is linear and injective, so its derivative is injective. Composition of injective maps must be injective. So d of iota at the point x is injective. Because this holds at any point x in M, this implies iota is an immersion. So it remains to show iota when you kind of restrict its codomain to the kind of image of iota is homeomorphism. If you do that, you get it's an embedding. I leave that part to you. The second step, so the first definition implies the second definition. Now we should show the second definition implies the first one. So if M is a submanifold of N in the embedding sense, we should say M inside N satisfies the local modeled description. This one is slightly more challenging. Okay. Okay. So let's see how we are going. What is the strategy to prove that? This statement that second definition implies the first definition follows from something called local immersion theorem. So local immersion theorem almost immediately proves this. And it's kind of stronger, more general result. Local immersion theorem says when you have a smooth map F from M to N, M and N dimensional, that this map is an immersion, not even an embedding, just immersion is enough. It's immersion at a point X in the domain with Y, the image of that, F of X in N. Then you can pick charts, let's say phi, some chart, some coordinate map around X, and psi, some chart or some coordinate map around Y. such that in these coordinates, f has a very, very simple description. So f in these coordinates, by definition, is defined to be psi of f or phi inverse. As a map from Rm to Rn, it's given by the canonical immersion. So that's the description of local embedding theorem. So it means psi of f of phi inverse acting on x1 up to xm is given by x1 up to xm, and then again 0 for all the other components, right? So just schematically, let's say this is M, this manifold is M, and this manifold is N, right? Let's say we have some immersion F, immersion at the point X, and here we have Y, which is F of X. So it says there is some open set around X and a map phi to Rm, and some open set around Y and a map psi to Rn, such that when you look at this composition where you first go up with phi inverse, then f, then psi, you get a map from Rm to Rn. This map from Rm to Rn is given by this model. The model is this canonical immersion. So that exactly means definition 2 implies definition 1, because if you take f to be the inclusion map, it says because it's immersion, it must be given by the canonical embedding, which is what describes the local model. So the whole point is that we should find phi and psi, right? If we prove the local immersion theorem by finding suitable phi and psi, by just letting f to be iota, we get what we want. Okay. So so in order to show second definition implies first definition, we need to prove the local immersion theorem. So what is the key thing to do? What is the key statement to prove local immersion theorem itself? It's something quite well known. It's the inverse function theorem or the implicit function theorem. So the main or the key idea to use to prove local immersion theorem comes from calculus. In fact, inverse function theorem is very, very fundamental in differential geometry. So it would be good to kind of review that more carefully and make sure we understand it. So we need to set up a definition before stating it. So recall, we say a map F, smooth map F between two smooth manifolds X and Y is a diffeomorphism. We said F is a diffeomorphism. If it's injective and surjective, which simply means it's one-to-one, one-to-one, F is smooth. Also, F inverse should be smooth. So both F and its inverse, they should be smooth, right? That was our definition of diffeomorphism. Great. Now we have a new definition called local diffeomorphism. So suppose G, again, is a smooth map between two smooth manifolds X and Y. We say it's a local diffeomorphism at diffeomorphism at a point X. Say we have a point X in the domain, and let's say Y is G of X in the target. We say G is a local diffeomorphism at X if there are two open sets U and V, where U is an open subset of X containing the point X, and V open subset in Y containing the point Y, such that if we restrict G to this open set U, we would get a map from U to V, and this map is a diffeomorphism. So in other words, G doesn't have to be a diffeomorphism, but if you make its domain very, very small around X, you would get a diffeomorphism. So it's good to note that if a map is diffeomorphism, it must be a local diffeomorphism too. So diffeomorphism implies local diffeomorphism. The converse is not correct. You can have a map which is a local diffeomorphism at every point, but it's not a diffeomorphism. So a simple example would be a map G from R to S1 to a circle. E of t is defined to be it. So it sends R to S1 and it kind of wraps around S1 infinitely many times. So it's not one-to-one, and therefore it's not a diffeomorphism. But any point you pick in R, you can pick a very small interval over that and very small interval over the image of that, such that on these two very small intervals, G is a diffeomorphism. So G is a local diffeomorphism, but not a diffeomorphism. Okay, great. Having this definition at hand, we can define inverse function theorem. So let me first write something which is not inverse function theorem, but it's more kind of easier and straightforward to understand. Suppose G is a is a smooth map between two smooth manifolds. Suppose it's local diffeomorphism at a point X. So let's say it's a local diffeomorphism at X in the domain, with Y being the image of X in the target. So the point is that if you look at derivative of the map G at the point X, we get a linear map from tangent space of X at X to tangent space of Y at Y. So derivative of G at X is a map from tangent space of X at X to tangent space of Y at Y. So if G is a local diffeomorphism at X, this turns out to be an isomorphism between these two vector spaces. This is not the inverse function theorem, but in fact it's closely related. So the inverse function theorem essentially the converse of this statement. This is the other direction is also correct. So suppose you have a smooth map G from X to Y such that its derivative is an isomorphism, then G must be a local diffeomorphism at X. So in fact it's if and only if. Okay, so let's correct this. So let's say G is just smooth map. It's local diffeomorphism if and only if its derivative is an isomorphism. Okay, great. So local diffeomorphism using inverse function theorem, kind of this would reduce to just checking derivatives and isomorphism. This is actually quite strong theorem because deciding if G is a local diffeomorphism or not at some region or at some point is a complicated geometry question. But checking if the derivative as a linear map is a linear isomorphism or not is a linear algebra question. You can just look at the matrix, take the determinant to see if it's zero or not. So the inverse function theorem is reducing a geometric problem to a linear algebra one. Okay, let's go back to local immersion theorem. So we wanted to show if we have an immersion from M to N, if it's immersion at the point X, we can find charts phi and psi such that the description of f in these coordinates, which means psi of f or phi inverse, is given by this canonical form. So we are looking for some phi on M and some psi on N around Y, such that the composition psi of or phi inverse is given by the model. So we are looking for phi and psi, right? Okay. So we should find phi with suitable charts, suitable coordinates, phi and psi. Diffeomorphisms from a neighborhood of X to Rm and a neighborhood of Y to Rn. Okay, how can we do that? How can we find these maps? If we find these, we finish the proof. That's essentially the thing. Okay, so just let's go back and think about M and N. They are smooth manifolds, right? And just because they're smooth manifolds, any point in M or any point in N, they have kind of charts around them, right? So just pick any arbitrary chart for M around X and pick any arbitrary chart for N around Y. Let's denote them with phi tilde and psi tilde. So phi tilde is any diffeomorphism on a small neighborhood of X in M to Rn, and psi tilde is a given diffeomorphism of a neighborhood of Y in N to Rn. We just pick two arbitrary maps, right? We look at this composition, right? Psi tilde O F O field inverse. This is a map from Rm to Rn, or maybe a subset of open subset of Rm to Rn. This doesn't matter at this point. So let's just call this map G. Let's define G to be this map from Rm to Rn, let's say, which is not necessarily our canonical immersion. Okay, so the strategy is to modify phi tilde and psi tilde to get new diffeomorphism phi and psi such that psi of phi inverse becomes the canonical map we are looking for. So we should find a way to kind of correct this phi and psi. Also, without loss of generality, we can assume phi tilde takes x to 0 in Rm and psi tilde takes y to 0 in Rn. The reason is that if that's not the case, you can just look at composition of phi tilde with just a linear transformation. It preserves the mapping diffeomorphism. So assuming that's the case, derivative of g at 0 is a linear map from Rm to Rn. Its derivative, just by chain rule, is d of phi tilde, O d of f, O d of psi tilde, O d of f, O d of phi tilde inverse. The point is that evaluated at correct points. D of phi tilde inverse at 0 is, again, it's a local diffeomorphism, so this map should be an isomorphism, therefore it's injective. D of f is injective because f is immersion, d of psi is injective. Composition of injective maps should be injective, so d of g at 0 is injective. So just to say it again, derivative of g at 0 is a linear injective map from Rm to Rn, right? Okay. So from linear algebra, we know any injective map from Rm to Rn in a good basis, or say after a change of basis, has a very, very simple form. So in a good basis, the matrix that defines this map is given by a matrix which has an m by m identity matrix up there, and then lower block is just all zeros, n by m, n minus m by m matrix of zeros. Okay, so if you don't remember this theorem or you're not happy with your linear algebra background, you might want to go back and or try to prove it yourself. This is quite straightforward. Okay, so the main function we are going to use to modify phi tilde and psi tilde to get good phi and psi is defined to be this G. So define G to be a map from U times Rn minus m to Rn, where U is an open subset in, say, Rm, which includes 0. So the whole domain is a subset of Rn. So we define this map G. This is like the key definition of the proof. We define G of a point x and z, where x is in Rm, so it's given by x1 up to xm, and z is in Rn minus m, so z is given by, say, xm plus 1 up to xn. We define the value of G on this pair to be G of x, G of the first m component, plus 0, and then z. So the 0 is also 0, 0, 0, m times, right? It's 0 in Rn. So this sum is something in Rn. Let's define the map G this way. Okay. So what's the point? If we look at the derivative of G at 0, what are we going to get? So it would be derivative of small g at 0 plus derivative of this map 0 and z. So derivative of g at 0 is identity 0 matrix plus derivative of 0 and z would be 0 identity matrix. Their sum would be just the identity matrix on Rn. It's n by n identity matrix. Okay, so let's recap. We have a map G. Its derivative at 0 is a linear map. Its matrix is given by the n by n identity matrix. Identity is an isomorphism. Now we learned the inverse function theorem. Inverse function theorem says if the derivative at 0 is an isomorphism, on a small neighborhood of 0, G must be a local diffeomorphism. Right. Great. So G is a local diffeomorphism at 0, or it's a diffeomorphism on a small neighborhood of 0. Okay, great. This is essentially the key step of the proof. G is local diffeomorphism. What other things do we know about G? First, let's remember we defined the function G to be this composition: psi tilde OF or phi tilde inverse. That was the first thing. We defined this other function G to be the sum of small g plus 0 and z. Now, let's compute this other quantity. Let's look at composition of G and the canonical embedding iota. So iota takes x1 up to xm. Sorry, it's just acting on x. Iota takes x1 up to xm and it sends it to x1 up to xm, 0 for the rest. Just define iota to be this canonical map. So first, iota would act on x, we get x, and 0 for the rest. 0 sits on the place of z. So by the definition, this would be g of x plus 0 and z, but z is 0 here, so it would be just 0 and 0. So the sum would be g of x. This implies this composition equals G. This is the other thing we know, the other relation we know between these two maps. Okay, great. Why is it good? Why is it good? How can we use this? Okay. So the essential thing here is that if we go back to our setup, we want to find phi and psi, right? We want to find good phi and good psi such that psi OF or phi inverse is the canonical map. G is a local diffeomorphism. Psi tilde is a diffeomorphism. Therefore, psi tilde inverse is also a diffeomorphism. Therefore, the map psi tilde inverse OG is also a local diffeomorphism. It's just composition of local diffeomorphism. So on a sufficiently small open set, it's a diffeomorphism. G takes Rm to Rn. Psi tilde inverse is a map from Rn to n. So psi tilde inverse OG is a map from Rm to n. And local diffeomorphism at 0. So if you look at psi tilde inverse OG inverse, it's a local diffeomorphism at y from n to Rm. And this map is exactly what we should be using as our psi. So it is a diffeomorphism on a small neighborhood, on a sufficiently small open neighborhood, open set, which contains y in n. So the claim is that this is the correct chart to pick instead of psi tilde. So the phi we define is the same as phi tilde. We are not going to change phi tilde at all, but the psi we are going to choose is psi tilde inverse OG, the whole thing inverse. So the claim is that these two kind of coordinate maps, these two charts, they give us the canonical map. So the claim is that the map defined by psi OF of phi inverse is, which by the definition is psi tilde inverse OG inverse OF of phi tilde inverse equals the canonical embedding. Okay. Or canonical immersion, they're essentially the same thing. Okay, great. So iota. So this is what we want to prove. And this is a map from Rm, or an open subset of Rm to Rn. In fact, the map extends to all of Rm because it simply sends x1 up to xm to x1 up to xm, and again, 0 for all other components. Okay, how can we prove this? Let's write this again. This actually just follows from definition and the two equations we observed earlier. So we want to prove this equation. Psi tilde inverse OG inverse OF of phi tilde inverse equals iota. So note that this is correct if and only if I apply psi tilde inverse OG to both sides of this equation from left. So it's just like bringing this to the other side, right? So proving one is equivalent to proving the other, okay? So why is this one correct? Why is this one any easier? Well, look at phi tilde inverse. I can, well, look at psi tilde inverse. I can apply psi tilde from left side again on both sides of the equation. I get psi tilde OF of phi tilde inverse equals G O iota. So the statement is correct if and only if I have this, but G O iota is G by the equation we saw, and phi psi tilde OF of phi tilde inverse is G by the definition. So these are equal. This proves the equation we have up there is correct, which proves local immersion theorem. And as mentioned earlier, local immersion theorem shows the second definition implies the first definition. Okay, I guess this is a good place to stop this lecture. In the next lecture, we will discuss Whitney's embedding theorem.